Hello everyone. Now we'll see the second chapter, which is about the embedded system architectures. So mostly in this chapter, we'll cover the hardware parts. So earlier we have seen in our previous lesson some of um, the definitions of this embedded system and definition of real-time system, some of models and different scheduling algorithms. So now we'll see the hardwares which are required for designing certain kinds of these real-time and embedded systems. Mostly we'll focus on the architectures. So to begin with, we will see the hardware architectures, which is mostly referring to as ARM Cortex M0 Plus, which is the hardware overview, and the communication ports, different ports which are available to make those hardwares communicate with each other. And these microcontrollers, which were what we call ATmega32 microcontroller architecture, and it uses either of the two languages for writing certain kinds of programming to these hardwares. So assembly language programs and programming in C. Preferably, we can use either of the language. So we'll see each of the concept here. When we start with definitions, obviously we have defined embedded system previously, and now we'll see embedded system architectures, which refers to the design and organization of different hardwares and software components within embedded system. So this embedded system is a computer system which is designed to perform specific functions within a larger system. So usually dedicated to a particular task and tightly integrated with hardware that controls it because it is embedded into a larger systems. So when we see the architecture of this embedded system, it is centered around this microcontroller, mostly the microcontroller, which is considered to be the brain of the hardwares, which allows the other bigger hardware to perform specified functions. And this is sometimes called microcontroller units or MCU, which is typically a single integrated circuit containing the processor, RAM, flash memory, serial receiver, and transmitters, as well as other core important components which are used in traditional hardware systems. For example, uh, these MCU have integrated all those into a single component. But as for the traditional computer system, for example, we do have RAM separately. We do have flash memory, serial receiver, transmitter, all other components in a separate way into a single board bus. So what integrates them is the board. Here we have a smaller component called MCU having all the other components. The larger components in the traditional systems have them in a single board. So this microcontroller architecture are classified into two architectures mostly, the Harvard architecture and the Princeton architecture. So mostly they are almost look similar, but the difference is in their memory structure. So when you see this Harvard architecture, they do have a separate program and data memories. So one memory contains only the program code, and while the other memory contains only the data. So it allows single clock cycle, which is very sufficient for the operations to be performed because we are using a separate buses to access the code and data simultaneously. Because of this, single clock cycle is enough for these kinds of architecture. For instruction pipelining, it's very easy and has improved performance since it only uses a single bus. Somehow, when you consider the design, it's a complex kinds of design. When we see this Princeton or one-man architecture, they do have unified program and data memories. Single memory contains both program code and data, and processors needs to fetch code in a separate clock cycle and data in another clock cycle. Because of this, it requires two clock cycles. And again, we do have a simple design here, which is a kind of a bit different from that of the previous architecture. So when we see the figures, the Harvard architecture, for example, here we do have code memory and data memories, which are communicating with the central processing units. So each of them uses different data buses. You see, the data bus for transferring code information to the CPU and data memory to the CPU, address bus, as well as the control buses. But here, as you can see on von Neumann architecture, the code memory as well as the data memory both interacts with the central processing unit using a single data bus line, address bus, and the control bus. Because of this, their time and clock cycles are a bit different, and as well as the complexity. For example, here you see on the Harvard architecture, the complexity is somehow visible, but here it's not in Monument, so the complexity is um, a bit complex, and here in Harvard, it is simple designs that are visible here. Uh, the common hardware used in these embedded systems. Okay, so microcontroller unit is one of them. So they are widely utilized in embedded system due to their integration of microprocessors, memory, and peripheral, which is found to be on a single chip. So we will have a single device having all the components necessary for performing what a single microcontroller unit can perform. So they are mostly cost effective, power efficient, and suitable for applications with lower computational requirements such as home appliance, consumer electronics, and small scale industrial control systems. The other types of this microcontroller is this system on chips, which is an architecture having a combined microprocessor core with a range of components, including memory, graphics, processors, and specialized electrodes, and various peripherals, all integrated into a single chip, still similar to that of the microcontroller units, but having a different architectures, combination of these processors, and they provide high performance and flexibility compared to these microcontroller units, making them suitable for more demanding applications such as smartphone, tablets, and automotive systems. And some of the advanced industrial control systems utilizes this system on chip architectures. Field programmable gate array. So mostly they offer programmable logic resources that can be configured and implemented to customize digital circuits. So they are highly flexible and can be reprogrammed to adapt to different functionalities. And they are commonly used in applications that require real-time processing, high-performance computing, and complex signal processing, such as aerospace, telecommunications, image or video processing, which is used for communicating. For example, our TV, our remote, and our decoders. So mostly the process using these field programmable gate array technologies. And the other one is this digital signal processing. They are specialized microprocessors designed for efficient digital signal processing tasks, including audio and video processing, telecommunication, and control system. They have dedicated hardware components and instructions optimized for numerical computation as well as data manipulations, which makes them well suited for applications that require real-time signal processing. Uh, Application specific integrated circuits. This is another hardware. So they are custom designed chips that are specifically tailored for a particular applications. So they offer high performance, lower consumption, and can be optimized for specific tasks. So they do have a fixed configuration after production, and they are once used, they cannot be reprogrammed. System in package. They are referred to integration of multiple chips and components into a single package. So this approach allows for combination of different technologies such as integrating microprocessor with memory, sensor, and wireless communication modules. So these provide compactness, improved performance, and reduced power consumption, making it suitable for miniaturized embedded system, wearable devices, and Internet of Things applications. And we have mentioned a lot of these kinds of hardware architectures. So the choice of those hardware architecture depends on different factors like the application requirements, the performance need, power constraint, cost consideration, and development resources available out there in your surrounding. So based on that, you can preferably use each of them based on those factors. So mostly the designers evaluate those factors to select the appropriate device architecture, which meets specific needs of those embedded systems. So when we see the ARM Cortex M0 Plus, so which is mostly split broadly into three main categories. So ARM, which is a profile. Each of them has a profiles. So for example, A is a profile mainly for applications. R is for real time, and M is for microcontrollers. Okay. So based on this, Cortex A stands for applications. So application processor cares calls for a performance intensive systems. So mostly if you are requiring to have application intensive or performance intensive, so we will prefer to Cortex A. So there are different processors ranging from A5 to A7E. So which is based on the ARM version 7 A architectures. So this Cortex R, the other architecture is Cortex R, which is preferably used for high performance. Okay, those cores are mostly if you are having tasks which are performance intensive, so we'll prefer to use this R Cortex profiles. And M, which is microcontroller cores for a wide range of embedded applications, mostly Cortex M0, M, M0 Plus, M1, which implements ARM version 6 M, version 7M, and version 8 M's are there. So each of them do have different categories of applications and performance capabilities. So based on the requirement, we'll prefer to use each of them based on their requirements. The hardware features and the components commonly associated with these M nodes, mostly their parts like port GPO for general purpose input output, their registers, which is referring to the memories. So they are classified into three. So general purpose registers, special purpose register, and system control registers. Each of them do have their own function and preferably different performance capabilities they have. And the other parts are analog inputs, outputs, and analog to digital converters, digital to analog converters, Those are the very important parts in general cortex M0 class. So we do have ports, GPO, registers, analog to digital converter, and digital to analog converters. Those are the very important components of these hardwares. When we see these ports and GPOs, so this Cortex M0 provide a set of GPO, general purpose input output pins that can be configured as either input or outputs. So on the hardwares, there are different pins which we configure either uh, as an input or output. There are different numbers and letters on the hardware. So based on the input that we provide and based on the connectivity we have, so we'll configure them uh, in our programs and in our hardware connectivities as an input or output. And the pins allow microcontroller to interface with external devices and peripherals. So the number of GPO pins available can vary depending on specific microcontroller chip that incorporates the core Cortex M0 core, ranging from I think 8 pins, 32, 64, 128. So if as the microcontrollers capability and performance increase, so we do have different numbers of pins which are incorporated into a single microcontrollers. So each of the pins are configured based on the requirements of the hardware and the performance that we have on our devices. When we see the registers, they include general purpose registers. Whenever we are using these kinds of registers, so they are used for data storage and manipulating different datas during the program execution. So that's what we call general purpose. Okay, special purpose registers. Okay, these are used mostly for controlling specific functions of the processor, such as program counter, stack pointer, control register for interrupt handling and system configuration. That's what they are referred to as special purpose because they are performing specific functions which are specifically performed by the operating systems. Like for example, when failure happens or interrupt happens, handling that interrupt is mostly done by the special registers, controlling of different operations. Okay, stack pointers, counting the programs. Okay, those are special activities performed under the operating system. So these kinds of activities are performed by special purpose registers. System control registers. So those registers manage the behavior and configuration of the microcontroller, including clock control, reset control, and power management. So those are performed by uh, system control registers. Analog input outputs. So the Cortex M0 itself doesn't have a built-in analog to digital converters or digital to analog converters. Because of this, digital inputs, analog input output datas. However, microcontrollers that incorporate those Cortex M0 core often include those peripherals as part of their overall system design. So, analog digital converter allows microcontrollers to measure analog signals from sensors or other analog sources, while the digital to analog converter enables the generation of analog voltage or current signals. Okay, so the signals that are coming from different hardwares like our sensors, cameras, or other devices are converted to digital and from digital to analog by using those two devices because the input should be understood by the system as well as by the users. And the other thing is this analog to digital converter, which is responsible for converting these analog signals into digital values that can be processed by the microcontroller. And this, the specific features and configuration of this Device vary between microcontrollers, including the number of channel, resolution, sampling rate, and input voltage ranges. Um, the other one is this digital to analog converter. So this device converts the digital values into analog signals, and it is useful for generating analog voltage or current output required for various applications like audio playback, motor control, generating reference voltage. And similar to analog to digital converters, the specific characteristics of these digital to analog converters can differ between microcontroller implementations. And as for communications, so mostly it's referring to the ports available out there, like parallel communication. For example, if you are having parallel communications, we can use the Cortex M0 Plus, which can be connected to the external devices using parallel communication interfaces. So here, general purpose input output pins are used for parallel communications. USB ports like serial bus communications, which are used and they can be integrated with the USB controllers, enabling the communication with other devices. USART, which is a versatile serial communication that supports both synchronous and asynchronous data transfer. And SPI, which is a synchronous serial communication interface, commonly used for short distance communications between different microcontrollers and peripheral devices. TUI or I2C, which is also known as I2C mostly, which is a popular serial communication protocol that uses two wires. That's why it refers to I2C, and it's having two wires for communication, a data line and a clock line communication. So if we are having an internet connection for our communication, so we will use Ethernet. Although the Cortex M0 itself doesn't have a built-in Ethernet, so it can be combined with external Ethernet controller or module which enables the Ethernet communication. So there are devices which support this Ethernet communication additional to the microcontrollers that we can use. So it's a module. We can connect them through pins and use our communication through internet. And the other device is this wireless communication. They can be integrated with various wireless communication modules such as Wi-Fi, Bluetooth, Zigbee, LoRa, or different wireless communication technologies. Also, they can also communicated through modules. So we might not have microcontrollers directly having these wireless modules. So you can connect them through different modules which support this, the way these device communicate. Uh, as for these AVR families and different port numbers and their naming, so we can see different types of AVR part numbers. For example, starting from ATMEG 128. So the AT refers to the AT mail, which is a mega group having a storage of flash 128K. When we refers to at 90s 4433, so we refer to at 90s or classical groups. They are referred to mostly the classical groups. They are having at meg 8, at meg 60, at meg 32, 64, and 1280. Each of the device supports the code ROM for each of the ATMEX and the data RAM, the EPROM, input output pins, analog to digital converter, and different timers are there. Or ROM, RAM, and EPROM memories are all the data are stated in bytes, and data RAM, especially for general purpose RAM, is the main amount of RAM available for data communication, and they are stated specifically in a table observable here. When we refer to the state of this atomic teeny family, so they are ranging from 1813 to 1884. So they do have a code ROM, data ROM, and data EEPROM, having inputs output pins ranging from 6 to 12, and analog to digital converters, uh, 4 to 8, and the timers 1 and 2, pin numbers and the package. Uh, the first atomic tin at tiny 30 having 8, and the other pins 18, 44, and 84 having 40 pins and different packets. So when we see a special purpose family, so they are referring to as at 90 CAN 128, at 90 USCB 11287, at 90 PWM 121K. So those are some of the categories of different AVR port numbers, and the way they are specifically named. So when we see at make 32 pin and their descriptions, so mostly the hardwares of the microcontroller units is having these kinds of architecture, and as you can see on the device, so we will have a reset button which clears the information on the microcontroller and restarts the device for execution of the programs written on the device. And VCC, which provides supply voltage to the chip, and it should be connected to 5 volt mostly. It doesn't support uh, the whole electrical voltage coming from the electrical outlet, which is not more than 5 volts. So if the power coming from electric source is more than 5 volt, so we will use a step down transformer and other modules integrated or connected to these microcontrollers. And these are the pins externals 1 and 2. They are used to connect external crystals or RC oscillators. If you are using maybe if you are connecting our devices with crystal oscillators, so those are the exact pins for connecting them with crystal oscillators. And this is for reference voltage, a ref. So they are stated as A for stating the ports are sorry. So the ports are ranging in A side mostly, as you can see, port A0 to port A7, and the reference voltage is also in the A side, so that's why it's referred to as reference voltage for analog to digital converters. Um, that is a VCC, which is supply voltage for analog to digital converter, and port S. You see, they do have their own power sources, so we can connect it to the VCC for having those ports of analog to digital converter power source. So if you see each of the parts, there are 4 ports: port A, port B, port C, and port D. So each of them can be configured separately having different perspectives or definitions and based on their performance, and the way we configure them determines how they function exactly with what is it should have to be performing on the hardwares. When we see this ATmega32 in 8 bits microcontroller from the AVR family, mostly which is developed by the Atmega groups. So the input output ports of the microcontroller has 32 general purpose input output pins, which is divided into 4 ports: the serial communication, the UART, analog to digital converter, and power management ports, which we have already discussed them in our previous discussion sessions. For developing these, we can use ATmega32, which is widely supported by the development tools, including integrated development environment like Atmel Studio, Arduino IDE, and yeah, as for those tools, provide user-friendly environment for writing, compiling, and debugging different cores for the microcontroller. So the ATmega32 microcontroller architecture, which strikes the balance between the performance, functionality, power efficiency, and making it suitable for a wide range of applications, including different industrial automation and consumer electronics, robotics, as well as so much more devices and technologies that are applicable. As for the programs, as we have tried to mention them on the start of our lessons, yeah, we can use assembly language, which is a label field which allows the program to refers to line of code by name, mnemonics or operands, and fields together to perform real work programs and accomplish the tasks exactly. So the comment field begins with semicolon. That's how the programs are written. Mostly we will see those concepts in our lab sessions. Again, first we use different editors, the way we save the programs and the codes. So those are mostly what we can see practically in our lab sessions. Thank you. Next time we will start the third chapter, which is the software framework for real-time and embedded system. Thank you very